Good morning, students. Hope you've had a good break. Hope you guys have all been staying quite healthy. I have been. My wife and I are doing great. We're in my house right now, so welcome to my humble abode. Maybe I'll give you a tour later. Alright, so what did we end off with? I believe last time we ended off with momentum. Alright, we're now going to be talking about springs. Springy springs. There's a lot of different types of springs. We've got a couple here. I went to the hardware store, picked up a little bit. We got some that are kind of really hard to press. We've got some that are you pull on. Some of them that are really long and really hard to press, and you can also pull on them. And we got a slinky. You can consider this a spring, I suppose. Alright, so springs. Where do you see springs? No, you see them everywhere. You see them in your car. Actually, let's go see where you can find some springs. You can find springs inside of your bed. They keep your bed nice and springy and conform to your body. Springs in a door handle. See how it bounces back? You can find springs all over on a bicycle. See how they're on the little seat right there? You can also, they've got them inside of these handles. They've got them on these over here. Everywhere. You can even find springs in household items like pens or watches. I don't have a watch, or clocks. Clocks and watches have them. Now, you got basically two different types of springs. You got ones like this and like this. And these are called tension springs. Because when you pull them, it produces tension. Or these ones, you have to compress them. These are called compression springs. These ones you can also pull. You can pull it, or you can push it. This one's really hard to do. Okay. So, most springs and elastic things like rubber bands or bungee cords, they follow something called Hooke's law. All it is that the force from a spring, F, put a little S right there for spring, equals a negative K times an X. Alright, what do these variables mean? Well, force is the force from a spring. You can definitely tell with this one, you pull it, the harder you pull it, the more force it is.
So here we got the force of spring. Alright.
Now we got two other variables. X. X is going to be the distance that the string is stretched, that's a word, stretched or compressed from equilibrium.
So this is distance. Spring is stretched or compressed.
Okay, that's not too bad. K, what is K? We haven't really seen K before, have we? Well, we call it the spring constant. And what that basically is it describes how springy a spring is. So something like this, it's got a very low K, a low spring constant, because it's not very springy. I mean, what do I mean by springy? Well, springy, I mean, it's a property of the spring itself, of the material. Springs with large K values seem to be very thick and very hard to push, and they're very springy. Springs with low Ks, low spring constants, are very easy to stretch. Ones like this, one that I can just squeeze with my fingers. Oh, there it goes. So I'm not going to find that. That's fine. Those are very low spring constants. All right.
So we're going to call this our spring constant. That's how springy it is. Springy. All right.
Now, we have this negative sign right here as well. What does that mean, negative sign? Well, what that is telling me is that if I'm just stretch this spring in the positive direction, a positive x, which way is the force pointing? It's going to be pointing in the opposite direction. And that applies to all types of springs. So let's say I had one of these, I want to compress it in the negative direction. Well, the spring force is going to be pushing back in the positive direction. So they're always opposite. Okay, so let's do a little bit of an example. Okay, say that we have a wall and it's got a spring. We got Bob over here. And let's say this spring has a spring constant, K. This is the spring constant. And we're going to say it's equal to 300. Now, does that have units? It sure does. K values have units of newtons per meter. Okay. So we got this spring. We got Bob over here. And he's going to stretch this spring real far. All right. So he's going to stretch this spring, let's say, 0.5 meters. If we want to find the force, remember, force equals negative K times X. Now, is our X going to be positive in this case? Let's see. Let's set up our coordinates, where to the right is positive and up is positive. So in this case, we're going to stretch it positive to the right of 0.5. So our force is going to be equal to negative. Our K value is 300 newtons per meter times our distance we're stretching it by, which is a positive 0.5 meters. If you notice, the meters cancel out, and you're left with negative 150 newtons. Let's look at our Hooke's law equation algebraically. So force equals negative K times X. Now this looks a little familiar to me. This looks kind of like the linear equation. Y equals mx plus b. Now you notice, for our force equation, it doesn't really have a b. It doesn't really have a intercept to it. So we're just going to ignore the b here because, well, it's 0. For our force, our y is going to be our force, our x is going to be our x, and our slope, which is m, is going to be our negative k. I'm going to graph this. There's my y-axis. Here is my x-axis. Now, what are we going to see? Well, we're going to see a linear relationship between force and x, the distance is displaced, which makes sense because the more you stretch a spring, the harder it is to pull, so the more force it has. So, it's going to be a line kind of like this. And why is it negative? Well, that's because of the negative sign. Okay, so say we have a very stretchy spring. So something with a lot of springiness to it, with a high K value. That's going to result in a slope that is very steep. If you're going to look at it, say, the slinky, that's not very springy, not very stretchy, and so it's going to have a very shallow slope to it. Okay, so say this is our graph. We got to label our axes, so this is going to be force versus distance. Now, the more we stretch the spring, the more we're going towards our higher x values, the greater the negative force is going to be.
So as x goes up, our negative force goes up. Well, I mean, technically it goes down, but the magnitude goes up. Okay. Now I want you to recall from when we dealt with work. It had very similar graphs. Both this and the work graphs were force versus a distance. Now, if you remember for work, we found that if you take the area underneath a graph, take the area underneath the graph, you end up with energy. Okay, so this is going to be our area, which equals energy. Now, what kind of energy do you think a spring can contain? Well, we kind of learned about this before. It's called elastic potential energy. What that says is that the greater you stretch a spring or compress it, the more energy it's going to store. Think about like a bow and arrow. When you stretch a string back and the bow kind of folds in on itself, it stores a bunch of energy, and when you release the arrow, all that energy turns into kinetic energy. So how can you find out how much energy is stored? Well, when we dealt with work, we knew that it was just the force times the distance, or also known as the energy. So, if we're going to do the area of this curve, what's the area of a triangle? Well, it is area of a triangle equals 1/2 base times height. Okay, so the area of this triangle is going to be 1/2 of this base times the height here. So the base is just going to be x, and the height is going to be our force, which is just equal to k times x. So if we do the area, that's equal to 1/2 times the base, which we said was x, times the height, which is going to be kx. That leaves us with an equation of area equals 1/2 kx squared. All right, that's an important result. So the area, remember we said, was the elastic potential energy. So I'm going to write this over here as U, remember that's potential energy, of S, so that's spring potential energy, equals 1/2 K times X squared. So, what have we learned so far? We know two equations. We know that force is equal to negative times K times X, and we know potential energy of a spring is equal to 1/2 K X squared. These are important to know and to understand.
Alright guys, well, thanks for watching. Hope you guys stay safe. I'll see you in the next video, I suppose. And like, comment, and boop that subscribe button. I think that's what you're supposed to say at the end of a YouTube video. Alright, well anyways, see you guys later.